F3. On. And now you may think to yourself, didn't we have this in general chemistry? Right. But in order to make it useful for organic chemistry, we need to condense some things and combine the valence bond theory with the molecular orbital theory in order to make it useful. I mean, we can't in this course, or even in any of the courses I teach, we can't go into so much detail in the molecular orbital theory that you could actually go in and draw the molecular orbitals for complex molecules. We have to think in terms of valence only. Otherwise, I mean, it's probably 2 or 3 courses just to get that far. So we want something we can use. So this is just a review to begin with. The difference, what is the valence bond theory? Valence bond theory is, says, with its localized electron model, it says that the electrons in a bonding system belong to the atoms they came from. In other words, when you go to the dance with your partner, they don't dance with anybody else. I mean, you may share them for a few minutes, but they still belong to you. The electrons still belong to the parent atoms that they came in with, the neutral atoms. They are bonded in this molecule by overlap of orbitals and sharing the electrons, but they still belong to the parents. Now, that works for a lot of things, but there are places where it really gets you in trouble. And one of the tweaks that we had to use in general chemistry for the valence bond theory was hybridization. We're going to review that in just a minute. And I think we talked a little bit about that already. Remember that when we use the VSEPR model for determining molecular geometry, it all depends on the number of attached bonds, groups, bonds, and lone pairs. That determines the geometry around any central atom. So if we have our first example there is ethene. Ethene, each one of those carbons would have exactly the same hybridization. But they would be sp2. That gives you 3 equivalent orbitals to share in the bonding process. Okay. The other thing that's interesting about, let's see, if we had, I'm going to draw everything out. We had those 2 carbons, and we had hydrogens attached to them. Like that. This is a sigma bond. Sigma bonds are always on axis between the atoms, right? On axis overlap. So they're strongest. They're the strongest bonds. If you have occasion for a double bond, in other words, we remove 2 hydrogens, and we still got 2, 4, 6, 8, 2, 4, 6, 8 octets around the carbons, then this other bond is a pi bond. And the pi bonds overlap off axis. So they're not as complete in their overlap, and they're weaker than the sigma bonds. But the other thing that the pi bonds do is they fix everybody in their positions. There's no rotation. If there's only sigma bonds, then you can just spin till your heart's happy. But if you have a pi bond in there, you can't rotate the bond. It fixes the bond. And in fact, this trigonal planar, right, sp2 hybridization of that carbon gives you a carbon with, right, with 120 degrees, all those bond angles, and these are all in the same plane. Right? The way I've drawn this, all of those bonds are in the plane of the board. Whereas if we have just a sigma bond in our ethane, then they can rotate, and these hydrogens can be in, I mean, sky's the limit. Right? One microsecond, there's one sticking this way, and the next microsecond it's that way. Right, but that's tetrahedral sp3 hybridization. Well, while we're on the topic, say we take away another two hydrogens. And now we got a third bond, another pi bond. Right? You always have one sigma bond before you can have any pi's. Right? You gotta have the sigma, then you can have one pi, you can have two pi's. In this case, we still have the octet 2468 around the carbon. This is sp hybrid. And these are also in the same plane. And they will not rotate at all. There's no rotation here allowed. Pi bonds fix the molecule against rotation. That's a cardinal rule in organic chemistry. So when each one of these covalent bonds forms, most of the time, but not always, one atom comes in with an electron available, and the other one comes in with another electron available in their respective atomic orbitals, and they overlap. And they form the bond. So when they form that bond, now there are two electrons in that bond. So any bond is two electrons. So this is two electrons, two electrons, two electrons. There's 6 electrons between these carbons in the bond. And they simply overlap their orbitals. Here are the atomic s and p orbitals. That's what they look like. Right? The s orbitals are spherical, remember? And the p orbitals have lobes pointing in 3 different directions. Right? The x, y, or z orbitals. Those are the p orbitals. When we overlap hydrogens, we get the green is a representation of what happens when after the bond forms. Now we have 2 electrons in that bonding sigma orbital. If, on the other hand, we try to bond carbon with hydrogens, depending on how many hydrogens you add, if you're going to valence bond 4 hydrogens with carbon and make methane, remember the argument for hybridization. What's the electronic structure for carbon? It has what? 6 electrons? Yeah. 6.
Yeah.
That's 6. So it's a 1s2, 2s2, 2p2 is its electronic structure. Right? Brings back bad dreams, right? Well, the bonding takes place with the valence electrons. This has one type of geometry, that has a different type of geometry. Now we know from experiments that the angles here are all the same. The bond lengths are all the same. The bond strengths are all the same. We need 4 equivalent orbitals. We can't use these 2 orbitals and those 2 orbitals to give us that structure, right, in a tetrahedral arrangement. So that's why this has to be hybridized with, we have 3 p orbitals here and 1 s orbital. Remember that? Right? 1 up, 1 down, up, and up. So we hybridize 1, 2, 3, 4 of those, 1 s and 3 p's to give us 4 hybrid orbitals. Remember that? You don't remember that?
I'm a little confused. I didn't understand. This is a good one. Be quite honest.
Oh, okay. Do you know how to write the electronic structure for a neutral atom?
No.
You don't? Okay. You need to at least learn it for carbon.
Okay.
If carbon has 6 protons and 6 electrons,
Mhm.
then the order in which they go in, the principal quantum number, 1, only has one subshell, the S. Right. So N equals 1, then L can only be 0. Right? This is N minus 1. It can go up in order. Say if this is 2, then it could be 0 and 1. Right? And we give these letters. That's an S orbital. If N equals 2, then we can have a 0 and a 1. So we can have S's and P's in that principal quantum number. So the available orbitals for carbon would be 1s, 2s, and 2p's. And we have 6 electrons. We can only have 2 in the s orbital, because one has to be spin up and the other has to be spin down. And the level 2 can have a 0, 1. This can have 2 in it, spin up, spin down. But the p orbitals can have 3 subshells, because this p can have an m sub l quantum number of -1, 0, or +1. Right? Go negative as far as you go, and then work your way up one at a time until you get positive. So if it's 1, it can go -1, 0, +1. If that were 2, it'd be -2, -1, 0, +1, +2. That would be d orbitals. But the p's can have 3. And each one of these can have an m sub s of +1/2, -1/2. So you can have 2 electrons in each one of these, maximum. Well, we only have 2 left over, right? We've used 2 of them off already. 1, 2, 2 orbitals up with 4 electrons. So we only have room for 2 more. And they have to be unpaired, right? That's Hund's rule. Hund says you have to put at least 1 spin up in each one of these subshells before you can start pairing. Okay, so and this is the valence shell. That's the one, the valence is the one that's involved in bonding. That's a valence bond theory. We can ignore this one as a core. This is core. This is valence. That's where the bonding takes place with the valence electrons. Okay. The shape of an s orbital is spherical. Right? The shape of a p orbital is lobed. Right? One in this direction, that direction, or in this direction. That allows for 1, 2, 3. 1, 2, 3. Okay. But if you try to bond a hydrogen with this one, it's non-directional. So I can go anywhere. If you bond it with here, it can only go this way, or that way. And that doesn't fit the reality of methane. Or carbon tetrachloride, same thing. You can't get the structure from these 2 atomic orbitals. So that's when hybridization was invented by Linus Pauling. He said, okay, why don't we just mix these together and come out with 3 equivalent orbitals, or 4 equivalent orbitals? Well, you got 1, 2, 3, 4. You need 4 orbitals that are actually the same in order to get that tetrahedral geometry. So we hybridize 1, 2, 3, 4 of these orbitals, and we get 4 sp3 hybrid orbitals. Okay, that's where we're at right now. So since we have now 4 equivalent sp3 orbitals pointing to the apexes of your tetrahedron, then a hydrogen at each one of those gives you exactly the tetrahedral arrangement. Right, and let's see, there. So we have carbon in the middle, hydrogen here, hydrogen in the back, hydrogen here, hydrogen here. That gives you that tetrahedral arrangement. Okay. Now that's the outline of the tetrahedron. The bonds are actually here. Like that. With a bond angle of 109.5 degrees. All the bond angles are equal. But experimentation has proven that. So the theory has to follow the experiment. Not the other way around. Okay, now where was I? Okay, we got that covered. sp3 hybridization gives you that tetrahedral structure. And the hybridization of sp3, let's see, I need some more room here. Let's see, I might as well erase it all. Now, as far as the shape of the orbitals goes, this is derived from the theory, right? The quantum theory tells us calculated shapes of the orbitals. They're not actually observed. The theory that is derived from the mathematics behind this quantum mechanics tells us that this is the most likely shape of the orbital, right? We're talking probability now. In other words, that's where chemistry has gone with their understanding of atoms and their bonds. It's based upon the mathematics and the most probable shapes of the orbitals. We actually don't know. Werner Heisenberg said, all right, you can't know both where it is and how fast it's moving. You can't know its energy and where it is. So you have to pick. And we usually pick energy because that's more useful to calculations. And then we say, all right, but then we have to rely on probability for the shapes, like where the electrons are. They're most likely in that sphere somewhere, or in one of those, or in those double lobes. But when you combine the two, the hybrid orbital, if you have a combination of one s and three p's, the shape is let's see, 25% like an s orbital and 75% like a p orbital. So it looks more like a p orbital. That's why the shape of that combined one here looks more like the p orbital. Whereas if you have an sp2 hybrid, now the shape is 50-50. Excuse me, no, it's not 50-50. Sorry. The S now is 33 and a third and 67%. When you get to sp hybridization, then you get 50-50. S character and p character. So it's starting to look more and more like an s orbital. So there you have the hybrid setup. The atomic orbitals on the left, hybridize them, then they look like this. And to give you, why does it say 2 sp3s? It should be 4. Yeah, that's a typo. There should be 4 sp3 orbitals, not 2. Okay, that's a mistake. Because you have to have the same number of hybrid orbitals as the atomic orbitals you start with. Right? That goes back to conservation of mass. You can't create, and you can't destroy. So you got to have the same number coming out as you go in. Okay, so when we form the bonds with these hydrogens and the carbon, we get this tetrahedral shape. right? And there's your one bond with the two electrons in each one. And they're pointing to the corners of your tetrahedron. And if we do the dash wedge setup, it looks like that first one on the left. Like this one's pointing out, that one's pointing back, this one's in the plane, that one's in the plane. All right. What was the question? I gotta uncover it so I can see what I'm doing. Apply valence bond theory to describe that bond between hydrogen and chlorine. Okay. What's the starting configuration of each one? Well, hydrogen's easy. It's 1s1. But since we're trying to bring you up to speed, right? If we're trying to bond hydrogen with chlorine, then the atomic orbitals look like this. Right? Just one electron in the 1s orbital. But chlorine is in that's in the second. No, it's in the third, right? It's in the third period, correct? Fluorine's in the second period, chlorine's in the third period, right?
Yes.
What is it, 17? Atomic number?
Fluorine.
17?
Yeah. Fluorine is 17. Yeah.
Okay. So if we draw out the complete, it's 1s2, 2s2, 2p6, 3s2, 3p, sorry, 5. Let's see, 4, 10, 17. There we go. So that's the complete structure. But we're only going to bond using those. All right. If we're going to bond hydrogen, it's only got one choice. It uses its s orbital. That's it. I have to overlap that 1s orbital with what? Well, in this case, all chlorine needs to make an octet is one bond. So we can bond with one of those p orbitals. Right? P, 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 X, Y, and Z. 1, 2, 3, 4, 5. We can use that one to bond with this one. Okay. So chlorine would look like this with our Lewis dot structure. Right. There's that lone electron in its orbital. It's a p orbital. Right. So this one comes in, and that's where the overlap occurs. And you've got these unbonded pairs still out there. We don't have to hybridize to get that structure. So that's what this picture is trying to show here. Right. You got the s orbital for hydrogen and one of the p orbitals. And you end up with this representation of the bond. Now that's, I question this one. Because what happens when you bond between two atoms, you tend to shift your probabilities of finding electrons into the bond, into this region between the two atoms. So there'd be less over here and less over here. But it's just a picture. So we'll have to go with it. How about this one? Where you're bonding a carbon with 3 hydrogens and oxygen's bound with a hydrogen. All right, the carbon, if you look at the carbon, how many bonds is required around the carbon? You got, let's draw it the way they draw it. This, that, with, yeah, those are hydrogens. You got this one in the plane. You got this one back behind. Okay. Then you got this one in the plane, with that oxygen. And that oxygen is bound to a hydrogen. Right? Make the octet. We have two bonds. Oxygen prefers two bonds with its two lone pairs. All right. So how are we going to bond those? Well, carbon's got 1, 2, 3, 4 groups around it. That means it's sp3 hybridized. Okay. Each of the hydrogens, of course, uses its 1s orbital. That's a no-brainer. How about oxygen? How is it hybridized? Well, it also has 1, 2, 3, 4 groups around it. So we would expect sp3 hybridization about it. But two of those lobes of the sp3 hybrid are occupied by lone pairs. That's what we're trying to show here. Right? Those lone bonding electrons are in sp3 hybridized orbitals, but they're not bonded. Okay. So what does that look like on an energy diagram? If we say, all right, what's the energy of each one of these? Well, bonding tends to lower the energy, right? So these would each be lower in energy. But these would be the same as they were before. There'd be no change at all in their energies. That's typical of lone pairs. They do not change their energies. Questions? I'm still processing. All right. So here we go with the ene types. Okay. We got a sigma bond and we got one pi bond. And around each one of the carbons, we have sp2 hybridized. Remember when we hybridize a carbon and get sp2 hybrids, we get this carbon and we get sp2 means we have 3 available bonding regimes. And then we have 1 unused p orbital. So we can come in here with, let's see, we're using hydrogens. We can come in here with a hydrogen and a hydrogen. And that uses 1, 2, remember, sp2 hybridized. They use 2 of those. And the other one is overlapping with this other one, this other carbon. That gives you your sigma bond. And so there's your p. There's your unused p orbital, right? We used only 2 of them to make that hybrid. So we got an extra p orbital sitting out there. Those p orbitals overlap. And that gives you the pi bond. Okay. Are you sure you didn't get this in general chemistry?
I didn't get the stuff with the overlapping, but we did a lot of the sp2, sp3.
Okay, that's good.
I don't know.
I'm in your 1 and 2.
Oh, we get this in the first semester though.
I don't remember if we did or not.
Yeah. Yeah,
It
we
was so
It's been a
tricky
while.
at first, but then as soon as I got it, it totally made
yeah, this hybridization occurred in my first semester course, occurs in the last 2 chapters that we covered in that class. So it would have been fresh. Okay. So this is what sp2 hybridization looks like, and you get the overlap in. I don't know why they keep saying 2 sp2s. There are 3 sp2s there. Oh. I know why the 2, because that's the principal quantum number. It's not saying how many there are. Okay, it's saying these S's and P's come from the second principal quantum. Okay, now I guess we'll give them that much leeway. But there are 3 of them. Because you put 1 S and 2 P's together, you have to come out with 3 equivalent hybrids. All right. And that means that the hybridized orbitals are in a trigonal planar arrangement. They could either be on the XZ plane, they could be on the XY plane, they could be on the ZY plane, but they're all in the same plane. So anytime you get sp2 hybridization and bonds with each one of those sp2s, those guys are all in the same plane. Right? So when we draw, well, that's kind of messy now. We draw it like this. And then we draw, let's see, yeah, they're doing like this. And then the wedge comes out this way. Like that. So we're saying this is in the board, these two are behind the board, and these are out the board. But they're actually all of these bonds are in the same plane. They're like this now. But if you pulled them out like that, they'd all be in that same plane. And that bond will not rotate. Okay. Let's see. Yeah, it's just okay. That's nothing new. What happens when we charge one of those carbons, make a carbocation out of it? Say if we have an sp3 hybridized ethane molecule. And we have one out here, one out here. Then we have one in the back, one in the front, and same thing. Actually, really doesn't matter because they're going to rotate like crazy. But if we could stop it for a split second, that's what it would look like. But this thing is going to be going like that. Anyway, this is sp3 hybridized. This is sp3 hybridized. It has 4 equivalent orbitals to accommodate those 4 bonds. Well, if we take one of those hydrogens away and both of the electrons with it, right, then what's our formal charge? The formal charge on this carbon would be how many valence electrons are in carbon? 4. And we are assigned 1, 2, 3, 4 to that. So this formal charge is 0. If we take one of those hydrogens away, then we have 4 to begin with, minus 1, 2, 3. So we have a +1 charge. Now we only have 3 groups attached to that carbon. That means we can only hybridize sp2 to accommodate 1, 2, 3 groups. Right? It's still got the charge, but the hybridization has changed because now we only have 3 groups attached to that carbon. And to make 3 equivalent groups in a hybridized system, you need sp2 hybridization and an empty p orbital. The empty p orbital is responsible for the plus charge. Still thinking on it?
Can you draw it in terms of the dashed lines and the arrows?
Yeah. Actually, that's the way it's shown there. Let's see.
Oh, okay.
Yeah, it's shown there with this one, and one of them's dashed and one of them's a wedge. And they would be in the same plane. Right. So if you draw, let's see, this one over here shows you have 1, 2, 3 groups, sp2 hybridized, and these would be trigonal planar. So the bond angle here would be 120 degrees. Whereas in the other carbon, the bond angle would be 109.5 degrees. So when we produce a carbocation in this case, you change the hybridization. Now that's going to be important when we talk about reactions. just to give you a clue. If the positive charge is here on that carbon, that makes it an electrophile. It's positive, so it's looking for electrons. But since it's planar, the nucleophile that has the electrons can come in from this side or that side. Either side, equally probable, which gives you a different type of isomer for the reactant. It comes from this side, and it's different. It's different enough to give us, and we'll talk about isomerization probably next week. Then attacking from one side gives you one type of isomer, attacking from the other side gives you a different type of isomer. That's where this is important. That's what I'm trying to do is say, we're not just learning this for busy work, to help us understand the reaction geometries. We got a triple bond. Now we got one sigma bond. You always have a sigma first, and we have two pi bonds. So the hybridization here, since there are two groups attached to each carbon is sp hybridized only. That means it has two unused p orbitals. One of them overlaps with the other one to give you a pi bond, and then the other one at 90 degrees from that overlaps to give you the other pi bond. I think we got pictures here. Yeah, what this is showing is these are hybridized orbitals, sp2, so there are two of them. One s and one p gives you those two, and these are unused p orbitals, and they are the overlappers that give you the pi bonds. Let's see, and they could look like this in any of the axes. What they're trying to show you there is the overlap of p orbitals that gives you two pi bonds. All right. So the bond angles, if you have an sp3 hybridized tetrahedral system, the bond angles are 109.5 degrees. Except when you have lone pairs involved, right? Then they do that ballooning pressure thing. But nominally, 109.5 for tetrahedrals, 120 degrees for trigonal planars, and 180 degrees for linear.
So the exact same thing that we learned in chapter 2.
Yes.
Okay.
This is repetitive. Okay, let's see. What's the question here? What's the hybridization of each non-hydrogen atom in this molecule? And uncover. And how many total sigma and pi bonds? Okay. All right. Well, let's draw the molecule first. We have this structure here. There's an oxygen there, like that. This is called a heterocyclic compound. Homocyclic means all the atoms in the cycle are the same, or in our case, usually carbons. And then heterocyclic, we substitute something else in there for the carbon. Oxygen, nitrogen, sulfur, usually. And then we got a double bond here, and then here, and then. All right. So here's a functional group. This isn't part of the question, but this is a functional group. This is a nitrile. Okay. All right. But to answer the question, we're asked how many sigma bonds and how many pi bonds? Well, the sigma bonds are easy. You just count up every bond in this thing that's not double or triple. There's 1, 2, 3, 4, 5, 6, 7, 8. 8 sigma bonds. There's 1 here, 2, 3, 4, 5, 6, 7, 8 sigma bonds. Okay. Pi bonds there's one here, and there are two here, one there and one there. That's a pi, that's a pi, that's a pi. So we have 3 pi bonds.
So every extra bond is a pi bond?
Yep.
Okay.
Right.
So if there was like another double bond, it would be 4. Okay,
Yep.
I understand that.
Okay, then we want to know hybridization. Okay, in order to do hybridization, we not only have to know the bonding atoms, but we have to know if there are any lone pairs in there. So here we have 1, 2, 3, 4. That's sp3 hybridized oxygen. This one, this carbon has 2 hydrogens. That's sp3. This one has 1, 2, 3. That carbon is sp2. That one is sp2. This one is sp3. 1, 2, 3, 4. This one is sp3. This carbon has 1, 2, only have 2 groups on it. This is sp. I better write those in. That's sp, sp3, 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 sp2, sp2, sp3. Now, how about that nitrogen? To make an octet on that nitrogen, we have 2, 4, 6, 8. It has a lone pair. And this one is sp3 hybridized. Oh, excuse me. No. Sorry. 2 groups. 1, 2. That's sp hybridized.
So it's just SP, not SP2.
Yeah, because that nitrogen has 2 groups. 1, 2, sp hybridized. This one has 1, 2, sp hybridized. Only this carbon has no lone pairs. That nitrogen does have a lone. Now let's see if I got it right. Let's see. All right. Starting over here. Yep, sp. Missed that one. Oh, it's pointing to both of them. Okay, both of them are sp hybridized. This one is sp3, sp3, sp3. Yes. These are sp2. That one's sp3. Okay, there it is. Now, they counted up last. They counted them up. They don't tell us how many sigmas and how many pi's. Did they do that before? No. They're leaving us hanging. Oh, they're counting them up separate, but they're not adding them up for us. Right. We did it right. Okay. Bond rotations. We already talked about that, but we're going to introduce the concept of cis versus trans. All right, we've all heard about trans fats. Trans fats can be produced in nature, but most often they're not. Trans fats are usually produced in a chemical plant somewhere where they hydrogenate natural oils. Natural oils, fatty acids in oils, are most often cis. So now I have to define what that means. You don't get cis or trans configurations with sigma bonds only because they can rotate, right? Their positions are not fixed. It's only when you get double bonds that you can use the cis and the trans terminology. All right. This just talks about rotation. When you only have a sigma bond, rotation is free. You can rotate all night long. But when you have a double bond, a pi bond in there, it fixes It can't rotate. Otherwise, you'll break the bond. I shouldn't say it can't rotate. If you do rotate, you break the bond. All right. So this just emphasizes the point that all of those in the orange or light brown, all of those carbons and hydrogens identified are in the same plane. Now, these down here, because they're attached by sigma bond, these guys can rotate up all they want. But these guys are part of the system that's locked in place with that double bond. So that's good to know for future reference where you can get rotation and where you can't get rotation. All right, now for the cis trans. Our example here is 1,2-dichloroethane. If we do like this, and then we say that, and that, like that, that would be the simplified version. And we would call this, right, 1,2 dichloroethene. Okay. Now that doesn't tell us about the positions of the chlorines. In this case, the chlorines, since we can't rotate that bond, then this would be different than if we wrote it this way. That would be a different molecule. We'll talk about that later, but this is an isomer. It's a structural isomer. In other words, it has the same formula, and this part of the name is exactly the same, but they're not in the same position. This is the cis arrangement. Same side. Chlorines are on the same side of the molecule. This is the trans. Opposite sides. Now, this terminology is trivial. Right? It preceded the current IUPAC standard. There's another IUPAC standard that allows us to avoid trip-ups that can occur with this type of arrangement. Right? If you don't have, right, in this case, you have hydrogens here and hydrogen there. There. What if you had something else in here? Like maybe bromine. Now the cis and trans, it gets a little murky because you're talking about, are you talking about the chlorines? Or are you talking about the chlorine and the bromine? So we need a new system that will come later. But as long as it's simple like this, cis and trans works. Right. So this one would be cis 1,2-dichloroethane. This would be ethene. This would be trans 1,2-dichloroethene. Now, when we talk about fatty acids, right, fatty acids are long chains, like that, like that, like that, with this carbon forming that acid. Okay, that would be a fatty acid. This one would be what we call saturated. There are no double bonds in it. But if you put a double bond in there and you put it in here like this, then this part of the molecule is on that side, but this is a hydrogen. And 1, 2, 3, 4, there's another hydrogen here. This means that this part of the molecule is trans from that part of the molecule. But if we drew it like this, let's see. That. Then this part of the molecule, this methyl group, is on the same side as that one, and that would be cis. So that's the convention for fatty acids. Not that you need to know it for the test, but you know, for future reference. And for fun at parties. Impress your party goer. you know, before they get too drunk to understand what you're saying. One other thing that we see from this cis versus trans arrangement, they have different physical properties. Right, one of those is mentioned here. In this case, the cis arrangement gives us a lower boiling point than the trans arrangement. Excuse me, higher boiling point. I'm sorry, higher boiling point. Why is that? You get more electron density on one side than the other by having both of the chlorines on that side. So it makes a more polar molecule than the trans. Trans tends to balance it out, make it less polar, which lowers the boiling point. Okay, how would we name this one? Well, let's name it by the IUPAC first. Let's see, we got a chlorine here and chlorine here, hydrogen there, and a methyl group here. Okay. So we want to take the longest carbon chain. 1, 2, 3, correct? That includes the double bond. So that would be,
Why won't we do 4?
Yeah.
Why won't we go all the way down to chlorine?
because that's not a carbon.
Okay,
We're looking for the parent.
okay,
Right.
okay.
Right, 1, 2, 3. So this would be, and we would start where it would give us the 1. So this would be propene, actually propene. We wouldn't have to say 1. 1, 2, 3. In that case, we have 2 chloro, actually 2, we have 1, 2, 1, 2, dichloro propane. Chlorine here, chlorine there. But that doesn't tell us anything about the geometry. Right? It doesn't tell us, because we could just as easily have written this with that name. We could write it with the methyl on the top and the chlorine on the bottom. And since it's a double bond, it won't rotate. Right? So there is a difference between that one and the one where we put the chlorine here and the methyl there.
You not need to say anything about the hydrogen.
Now, the hydrogen is superfluous at this point. Well, you could, yeah. Oh, sure. You could put the methyl and the hydrogen on the same side by doing it this way. Or you could put the methyl and the hydrogen on the same side by doing it this way. It's the same molecule.
But you wouldn't write it out.
No,
You wouldn't do 1, 2 dichloro, 1 hydrogen, or yeah, hydro,
no,
propene. Okay.
no. This tells you that this is a possible structure, but the other possible structure, put the chlorine over here and the methyl over there. So that's when we want to say this is trans. Oops. Let's see, is that the way they name it? They're not much help, are they? Oh, they just want us to tell whether it's trans or cis, aren't they? Yeah. Okay. This says the trans effect is on the chlorines. These 2 chlorines are trans to each other. If we put the chlorine over on the other side, we would write cis, 1, 2 dichloride.
But it's not caring about those hydrogens again.
No.
So it'll always be clear what
There-
it's wanting you to be saying.
Yeah.
Okay, cis or trans.
Yeah.
So
There's another way to write this, but I think that's the best way. I don't want to muddy the waters anymore.
So on the question, it says, does the molecule have 2 distinct configurations about the double bonds? That's like, I don't understand that question at all, like a regular.
Oh, distinct configurations.
Yeah,
This is one configuration. like that. We could also draw it like this. Since that bond cannot rotate, this is different than that one is.
And that would make it cis. Correct?
Yes, this would be cis. This would be trans.
Yeah.
That's what they mean by configuration.
Okay.
Since we haven't covered isomers yet, they should have, or once you get through isomers, then they can say distinct structural isomers. Structural isomers means that groups or atoms are moved in position. Right? They're attached to different carbons. Actually, these are not attached to different carbons. But it's still structural isomer. I'll explain that later. When we get to chapter 4 and 5. All right. Oh, there's our fatty acid, right? Alpha linolenic acid. Let's see. How many carbons is that? 16? 2, 3, 4, 5, 6. 17, 18. 18 carbons is the linolenic. And linolenic is an unsaturated, right? When they say unsaturated fats are better for you, that's what they mean. They got a bunch of double bonds in there, or at least one double bond. Some of them have 2, 3, 4. And there's a naming convention. There's the organic systematic naming convention, which is a real pain when you're talking about biomolecules. And then there's a biochemist's naming convention that is a little easier to handle. But we're not going to get into that. When they say alpha linolenic acid, a biochemist knows exactly what you mean and can draw that structure. So these bonds, these double bonds are cis. And the reason for that is we're looking at the carbon groups attached to them. Remember, anything that's not drawn is a hydrogen. And the carbons are where lines meet. So the carbons are where lines meet. Anything else that's not drawn is a hydrogen. So you have hydrogens on each one of those double bonds. There are hydrogens here. They're just not drawn in. And these are cis components, cis attachments to that double bond because it's on the same side.
Now, if you were to number that, where would you start at?
You'd start at the functional end. You start over here.
Okay.
Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9.
Okay.
So the first one will be a 9.
And those are still carbons, right?
Yes. Mhm.
You're starting numbering from where?
Right here.
One?
Right here, 1.
All right.
And this would be
There's I think on my exam I wrote that with a C under it. Whenever I wrote anyway.
just to keep it straight.
Yeah.
Yeah.
Something.
Sure, that's fine. But this is the carboxylic acid group right here. Don't include that one, just this one. 1 carbon, 2 oxygens, and 1 hydrogen. That's carboxylic acid. Okay. Okay. Oh, we probably should have got the models out, huh? Do we need to get the models out? You can tell from looking at it that you can't rotate them.
Yeah.
Yeah. If you have this molecule like that, then you need here, that. Right. 2468, 2468, 2468. So, 'Eight. 2, 4, 6, 8, 2, 4, 6, 8. So, what that model is showing you that, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, Um, these are in the same plane right here. Whereas these are in a different plane. So this one is to be like your anchor point. These two might be in the board like that. But these would be like that.
So those would be the lines.
Right, so we would draw these like
Yeah.
that
Okay.
to show that there were, and that's because of the way that the pi bonds have to be formed. When we form a pi bond here with p orbitals that are in the plane of the board, that's okay. But the other pi bonds are out, in and out of the board, right there. So that's why this one has to be rotated 90 degrees. And that's what the model would show you. Right. The way that model is laying there in the slide, we'd have to flip it over. Flip that model over and put these out here. The ones on the left there are the ones on the right here. Okay. All right, what are we trying to say here? As the hybridization of an atom goes from sp3 to sp2 to sp, its bonds become shorter and stronger. Okay, the reason for that is if you have that, actually there are two ways to look at this. If you have an sp3 hybridized atom, it can only have sigma bonds. If you have an sp2 hybridized, you could have one pi bond. If you have an sp hybridized carbon, you can have two pi bonds. That would shorten and strengthen the bonds. The other way to look at it is, what's the S and the P character of the hybridized orbital? If you have more S character, it's not as oblong like the P orbitals are. It brings things closer in, and bringing them closer in means shorter bond, stronger bond. That's two ways to look at it.
So repeat that again about the sp3 has only sigma bonds.
Right. Right. And the example there is ethane. The one on the left is only sp3 hybridized, and it has the longer, weaker bonds.
And then sp2 can have one
Pi bond.
one pi.
See, yeah, you got one pi bond here, you got a sigma and a pi. And that shortens the bond and strengthens it.
Yeah.
And then the sp2 can have two pi bonds, which shortens and strengthens further. But this also speaks down here to the S character of the hybrid orbital. Right? The S character of the hybrid orbital means it brings the bonds in closer, rather than being oblong like the p orbitals. And this is just another way of showing, as you go from the p orbital here, atomic orbital, s orbital, atomic orbital, and then you get the hybrids in here. The sp3s look more like the p's, the sp2s are kind of in the middle, and the sps look more like the s orbitals. That's all. That's the only purpose of that slide. Okay. Now, there's a concept called effective electronegativity. We understand from general chemistry the trends in electronegativity on the periodic table. And that's for individual atoms. And then we use that information to say something about a bond between two atoms. If they're further apart from each other in the periodic table, then the bond is more polar. And at some point it becomes ionic. But when you're talking about just carbon-carbon bonds with their attached hydrogens, we can say something about their electronegativities also on a molecular scale. When you have a single bond, then the electron density is confined between the atoms. That's a sigma bond. And there are also sigma bonds with the hydrogens. So everything is pretty much kind of a well mixed pudding, right? There's really no excess positives or negatives in that molecule. But when you get a pi bond, now you're pulling more of the electron density into the region between the carbon atoms. And since the molecule is a zero-sum game, it's neutral. Then if you bring more electron density into the central part of the atom, that means the outer parts where the hydrogens are located become more positive. So you've introduced an effective electronegativity for those hydrogens by introducing that pi bond. And that's why we show slightly more blue around the outer parts of these molecules, because we've concentrated more electron density in here. That makes this region more positive. Okay. So add another pi bond, it gets even worse, right? It gets even more blue or positive on the outside because we've concentrated more electron density in the center. That's what we call effective electronegativity. Now, I assume that increasing effective electronegativity of the carbon in this system changes the physical properties of the two carbons in this situation versus the two carbons in there versus two carbons here. So they should have detectable changes in their physical properties, like boiling point, freezing point, so forth. And their ability to solubilize certain things. All right. Let's see. In which A or B do you think the carbon double bond distances are longer? And in which molecule are the carbon-carbon bonds stronger? All right. I'm not sure I understand that question. Oh, we're focusing on the carbon-carbon double bonds. So which one's one on the left? We've got two double bonds in each molecule. Right? In the first one, the carbon double bonds are separated from one. So they'll definitely be shorter than the single bonds. But how do they compare to the double bonds in the other molecule? I think the shorter bonds will be in the B, because you've concentrated pi orbitals around that central carbon. I'm sorry, and stronger. Yes, shorter and stronger. Let's see if that works. Okay, what's the hybridization of each atom? Okay, we'll look at it that way. Okay. Yeah, okay. Yeah, actually, that makes more sense if we consider the hybridization. Right? The carbon atoms in the first one are sp2 hybridized. Right? There are three groups around each one of those carbons that are part of the double bond system. Right? That gives you a certain distance and bond strength. Whereas the carbon in the B example is sp hybridized. Right? It's only got two groups around. So those bonds should be shorter and stronger. Let's see if that works. Right. In A, carbon-carbons are sp2 hybridized. In B, each carbon bond involves one sp2 hybridized carbon atom and one sp hybridized carbon. Yes. Right. The sp2 hybridized carbons in B are the outer carbons. The inner carbon is sp hybridized. Has greater S character and thus shorter bonds, which means stronger. So the carbon-carbon bonds in B are shorter and stronger than they are in A. All right. So up to this point, we've been talking about valence bond only. Now we need to look at, ooh, it's 1:15. Am I out of time already?
Well, we go to 1:30.
Or 1:30.
1:30, okay. So bye-bye to the lab today. So, I don't know about your general chemistry courses, but did you talk about constructive and destructive interference? Didn't talk about those. Okay, so we need to go back to basics. When we consider particles, especially very small particles like electrons, what's been discovered is that depending on how you your experiment is structured, how you investigate the particle, sometimes it behaves like a particle and sometimes it behaves like a wave. For our discussion here and for the utility of the molecular orbital theory that's coming, I was searching for another term. Quantum mechanics, excuse me. For quantum mechanics, we consider electrons as waves, right? They're three-dimensional waves for sure, but it's difficult to visualize a three-dimensional wave, at least it is for me. So we use a rope that gives us a two-dimensional wave and use that as an analogy toward the three-dimensional. Now, the three-dimensional wave is really only described in mathematical terms. Schrodinger put together a whole bunch of equations that go together to make up the quantum mechanics. So when you see a wave traveling down a rope, right, you can do that. Actually, the waves, they draw it only as a hump, and that's okay. Right, you can put a hump in a rope. I used to do this in my high school class. I taught high school 1 year. That was enough. But I'd take a tightly wound spring that was part of the paraphernalia that I inherited, and tie it to a doorknob or a hinge on the wall, and then I'd set a wave moving and it'd go down and back. So I was demonstrating the movement of the wave. The string or the spring didn't move. I mean, it didn't change effectively where it was in space. Only the wave moves. So the wave is traveling down this rope in our example. And it can either have, in fact, I'm going to draw in this particular wave will always have a crest and a trough as it's moving. So this is positive displacement, negative displacement of the rope. Now, that's fine. And we can use this as an analogy for an electron. Not just the electron, but where we think the electron is, that probability approach again. Where is it, right? If we draw in where we think the electron is in terms of those orbital shapes, we're saying, okay, that's where we think the electron is. Where the electron isn't is called a node. So we draw in the nodes also. Now, when we overlap orbitals, now we're introducing what's called interference. So the wave of one electron is interacting with the wave of another electron. And it can interact in one of two different ways. It can constructively interact, right, in which our analogy would be like this. Right? So if this one's moving that way and this one's moving this way, when they meet, what is the summation of the two? Summation is bigger there, bigger there. That's not symmetrical, but that is a constructive interference. If, on the other hand, our waves are moving in such a way that this crest meets that trough and this trough meets that crest, then the summation of the two comes that. That's destructive interference. Does anybody have those noise canceling headphones? Okay. What they do is they measure the electronics in their headphones, measure any ambient sound that's entering. They have little microphones and they pick up the ambient sound and they generate a signal that's the same frequency, but opposite amplitude. So when they put together, destructive interference cancels out the ambient noise. They work exactly the same way. All right, when we look at orbital probabilities, oh well, okay, let me slow down. This slide shows you where the probability of finding an electron is and where it isn't. Actually, it's more difficult to see with an s orbital because it's spherical. But the 1s orbital has a probability of finding an electron with an s orbital is best if we draw it in a graph like this. And this is the distance from the nucleus. Probability of finding an electron that distance from the nucleus. This would be right at the nucleus. And this would be the, I guess, the probability. Let's see, is there a term? Is there a symbol for probability? I guess I'm going to have to use P. So for an s orbital, the 1s orbital, you don't find it right at the nucleus, right? That would be stupid. It just doesn't happen. It happens at a certain distance from the nucleus. So it would go up like this and then tail off like that. This would be 1s. For 2s, we get like this, and then it goes back down to 0, and then it goes up and then comes back down. So the 1s has a node at the nucleus, but the 2s, they all have nodes at the nucleus, but the 1s introduces another node in here. So if you looked at it in 3 dimensions, you'd have this shell, and then there'd be an empty space where there's no probability, and then there'd be another shell, spherical shell inside. It's more difficult to see with s orbitals than it is with p's. With p orbitals, you can draw those lobes like this, and you can see where the node is. That's what B is showing us. All right, so here's constructive and destructive interference. I got a video that I showed in my general chemistry class. I guess I didn't have time to incorporate videos in these slides. But it shows a wave traveling down a string, and then you have 2 waves approaching each other like this. Constructive interference gives you the one on the left. Destructive gives you one on the right. And then, let's see if the next slide says what I want to say. No, it doesn't. Okay, so if you tie one end to the wall like I did with that spring, and you send the wave down there, if you move closer as you make the wave, then you reach a point where you give it just a little bit of energy and the wave stands. It just moves up and down right there in that spot. It doesn't seem to move back and forth. It's called a standing wave. And it happens at a certain distance. For a half a wavelength will be a certain distance. And then at the next distance out, there'll be a whole wavelength. And then next distance, there'll be a wavelength and a half. Those are called harmonics in music. So the standing wave idea is actually where you should head when you're trying to understand destructive and constructive interference in electrons. Another way to look at it is when we draw the nucleus here, you got your positive charges and your neutrons, depending on the atom. And then you have this 1s orbital, the very lowest energy orbital. It's instructive to look at the standing wave of the electron at that region is exactly the right wavelength, if I draw this correctly. So that the waves are perfectly fit in that region of space. That gives you that first quantum level. Then if you move to the 2s level, you'll have the ability to put more waves in there. But they're always perfect. They don't come along and then not meet the ends. That would not be a standing wave. This is a standing wave. But when you overlap orbitals, then those standing waves from the two orbitals that are overlapping have to match in one of two ways. They have to constructively interfere and build up, or destructively interfere and tear down. When they build up, when they constructively interfere, you get a bonding orbital. And when they destructively interfere, you get an anti-bonding orbital. That's where we're headed in molecular orbital theory. Okay. All right. So we talked about that already. Remember, molecular orbitals are formed from the atomic orbitals of all the atoms that enter into the molecule. So the simplest way to look at it is two hydrogen atoms. So if you have energy on this scale, and you have one hydrogen atom here and one hydrogen atom here with each of their electrons, this one has a 1s atomic orbital with one electron in it. This one has a 1s at the same energy. There. When you form molecular orbitals, you have to come out with the same number of molecular orbitals as atomic orbitals that went in. Right? And when they go in to make the molecule, right? When they go in to make the molecule, then these atomic orbitals are gone. They don't exist anymore. Now we have molecular orbitals that belong to the entire molecule. I call it molecular communism, right? They belong to the collective. But when they do that, constructive interference gives you a bonding orbital, sigma bonding orbital at lower energy. Constructive interference gives you lower energy. Destructive interference gives you higher energy, and this is anti-bonding orbital. Okay, remember that? Did y'all talk about this in general chemistry? No? Okay, I'm hitting you with new stuff then. Okay, now that you've got the molecule, you put your electrons in, the same number of electrons you started with go into the molecule, and they follow the Aufbau principle. The electrons go in at the lowest energy orbitals first, and you start filling them up. So we've got two electrons here, and each orbital can hold two. They just have to be opposite spins. So now we have the molecule built of this one sigma bonding orbital with two electrons in it. Did y'all talk about bond order?
Yes.
Okay, good. So the bond order, remember the bond order is equal to the number of bonding electrons minus the number of anti-bonding. I bet you did have some molecular orbital discussion, because that's where this comes in. Divided by 2. So we have 2 bonding and 0 anti-bonding, so 2 divided by 2 is 1. 1. So the bond order roughly corresponds to single, double, triple bonds. So if the bond order is 1, it's a single bond. If it's 2, it's a double bond. If it's 3, it's a triple bond. The thing about bond order, though, is it doesn't have to be a whole number, right? You can have fractions. But this all results from constructive and destructive interference. And this thing can get really complicated in a hurry. The bigger the atoms, the more of them you have in there. This is what chemistry majors have to deal with. So as far as that goes, I'm glad I'm not a chemistry major. Because I would not want to spend a whole semester doing nothing but that. Okay. So this is called the linear combination of atomic orbitals. That's what we just did there. We combined atomic orbitals to make molecular orbitals. And this is an artist's idea of the bonding orbital versus the anti-bonding. And notice the anti-bonding orbital has a node between the atoms. Right? So it's just that. It's anti. It's against bonding. Now, why does molecular orbital theory, why do we even bother with it? Well, for two main reasons. One is the valence bond theory that here does not explain completely every phenomenon we observe in various compounds. For instance, let's see, I painted myself into a corner. I'm trying to remember the words. It's not coming. How molecules act in a magnetic field. Right? Are they drawn into the magnetic field or are they repelled by the magnetic field? And for the life of me, I can't remember the proper terms. But the molecular orbital theory explains how that behavior occurs. Also, the valence bond theory gives us virtually no information about energies. It's just a general approach to explaining how things fit together. That's it. It doesn't tell us what the energies are. Molecular orbital theory does produce energy values for bonds and for molecules. It's more quantitative in that respect. All right, so let's move on. We talked about the bonding molecular orbitals and the anti-bonding. The anti-bonding orbitals are always higher in energy than the bonding orbitals. And then there are the non-bonding orbitals. I mentioned those earlier. The non-bonding orbitals are the ones that really didn't change in energy between the atomic and the,
Have to run to
Oh, am I over now?
just by a few minutes, but I have to.
Okay, no, go ahead. It's recorded and I'll post it in Brightspace.
All right, thank you so much.
Sorry.
It's okay.
How am I doing? Can you tell me how many slides? Am I close?
Yeah, you got 1, 2, 3, 4, 5, 6, 7, 8, 9.
Okay. I'll try to hurry up. So there's another concept. When we have a molecule constructed of molecular orbitals, the highest occupied molecular orbital, that is the highest orbital, highest energy orbital with electrons in it is called the HOMO, the highest occupied molecular orbital. And then the one just above it that's unoccupied is the LUMO, the lowest unoccupied molecular orbital. Those are, and the distance between those tells you something about how the molecule behaves, both physically and chemically. If they're very close together, then you get the ability for electrons to jump between the two fairly easily. And that could say something about electrical conductivity, thermal conductivity, other properties, reactivity. Okay. This says something about the shapes of them, and we'll get into that later. Okay. I don't see any advantage to All right. If you combine an s orbital and a p orbital, then you get this odd shaped molecular orbital. This first one down here. It's not symmetrical because these two are not symmetrical to begin with. But if you get two of the p orbitals overlapping, you get more symmetry. And of course, the antibonding orbitals always have that node in the middle. They're working against the bonding. So the more electrons you can get in bonding orbitals, the better for the strength of your bond. All right. So for the hydrogen example I gave you, those were sigma bonding orbitals. You can also develop pi bonding orbitals. And usually, let's see, I'm trying to think of. Let's do something as simple as possible. How about dioxygen has 6 valence. All right, so if we start off with oxygen here, and we're going to make this diatomic molecule. We're going to leave out the 1s's, right? They do go into the molecular orbital system, but we're more focused on the valence system. So we have 6 electrons that are in p orbitals. So the oxygen is going to be, let's draw the whole thing out. 1s2, 2s2, 2p4. Yeah. So this is going to be s right here maybe. 2s, 2s. This is going to be 2p. How many p's do we have? We should have 3 p's, shouldn't we? But we don't have to hybridize. So where are our electrons? Well, from here, there are 2 in these here, and there are 4 in these. Okay. Okay. Now, what do we form here? Well, with these s orbitals, we get a sigma formed from the 2s, and we get a sigma star formed from the 2s. From these, we get, remember the p orbitals are on x, y, and z planes. So if we have 2 x's coming together, their overlap will be sigmas. Right? So 2 of these form the sigma from the 2 p's. And the sigma star, this is unbalanced, I'm sorry. The sigma star is very high in energy from the 2p. Then we get the pi from the 2p, and the pi from the 2p, and then the pi star from the 2p, and the pi star from the 2p. So let's see if we got the right number. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 molecular orbitals formed from the atomic orbitals. Now, where do the electrons go? Well, let's see. We got 1, 2, 3, 4, 5, 6. 12 of them together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That would be the molecular orbital structure for dioxygen. Notice the difference in energies. When we form bonds from molecular orbitals from p's, we get the sigma here and the sigma star very far apart in energy. And then the pi's fit in the middle. So the sigma star is from the p's is higher in energy than the pi stars. Now, scratch your brains. If you ever were introduced to this material, was there a discussion of SP mixing? Do you recall that? Okay, so we're not going to go there because SP mixing is really not going to be that important for us. And all SP mixing does is it takes this sigma and these pi's and flips it. I wish I could remember those words I was trying to think of. Oh, diamagnetic versus paramagnetic. The diamagnetic is opposed to the magnetic field. So the diamagnetic molecules will be repelled by the magnetic field. And the example that's used, the demonstration that's used, have you seen these huge horseshoe magnets? They're about this big. And they come up here and there's a strong magnetic field between these two poles. So if you take liquid nitrogen and pour it into that opening, it'll just go right on through. If you take liquid oxygen, it'll go in there and sit right in that magnetic field. That's because it has these unpaired electrons. Right? Paired electrons cancel their magnetic moment, but unpaired have that net magnetic moment that is capitalized on by the magnetic field, and it holds them in that field. Whereas dinitrogen has all paired electrons. Right? Dinitrogen would have 14, and the same structure would give you pair here and pair here, 2 more electrons. They're all paired, right? So nitrogen, when you pour it into that magnetic field, it goes straight on through. Okay, I can sleep tonight now. Okay, so I think what Dr. Carty is trying to do here is combine concepts of molecular orbital and valence bond theory. And when he does that, he's actually taking the valence bond hybrid orbitals from, in this case, 2 methanes, or these 2 carbons are sp3 hybridized. And then he's overlapping those orbitals to give him the molecular orbitals, rather than going all the way back to the atomic orbitals and trying to reconstruct. So we're going to the valence bond first and then making molecular orbitals out of that. Well, notice that how many bonding orbitals, how many bonds do you have in this molecule? 1, 2, 3, 4, 5, 6, 7. You have 7 bonds. Right? So once we've got those bonds formed, those hybridized orbitals going into a valence bond, then we can take those apart and say, all right, we've got 7 bonding orbitals. There must be 7 anti-bonding orbitals also. So we've got 7 sigma molecular orbitals in that molecule that's demonstrated there in the figure. But there are also 7 anti-bonding orbitals that have no electrons in them. Okay, that's the point of this one. What does it look like if we do a double bond? Well, in this case, we have 1, 2, it's sp hybridized. So we have 12 atomic orbitals that are being used in the sigmas. 1, 2, 3, 4, 5. Let's see. No, that's not right. 1, 2, 3, 4, 5, 6. I must be counting the hydrogens too. 12 atomic orbitals are going into 12 molecular orbitals. 5 of those molecular orbitals are occupied for sigma bonds. Right, you see 1, 2, 3, 4, 5. Those are sigma molecular orbitals. And then we have 5 anti-bonding sigma orbitals that are not occupied. So these have electrons in them down here. These don't. And then there's one that overlaps to make the pi bond. So that gives you a pi molecular orbital and a pi antibonding. And this pi bonding has electrons in it and the antibonding doesn't. That makes sense? Yeah, sort of. I understand. All right, I already gave you this information. The sigma molecular orbitals are typically lower in energy than the pi molecular orbitals, and the sigma star molecular orbitals are typically higher in energy than the pi stars. That's based upon this arrangement. If we go to ethine, or more commonly called acetylene, then we get only 10 atomic orbitals going into the sigma bonding system. And we actually have 2 pi molecular orbitals. Okay, so the way I look at this is, if you have, let me erase this, because we're going to stay focused primarily on carbons. So that's an advantage. If we have a carbon like that versus carbon like that versus carbon like this, right? And everything else on the outside. This only has sigma molecular orbitals and sigma star like molecular orbitals to deal with. This one has sigma and 1 pi molecular orbital to deal with. Molecular orbitals. This one has 1 sigma and 2 pi molecular orbitals to deal with. That's what I get from these last 3 slides. And that's correlates with 1 sigma and 2 pi's, 1 sigma and a pi, 1 sigma only. All right. Now, when we get to this methane molecule, CH3OH, oxygen in this case is hybridized, right? It's sp3 hybridized, but 2 lone pairs are in molecular orbitals that are at the exact same energy they were when they were in their atomic orbitals. So those non-bonding molecular orbitals now are the same energy as the atomic orbitals from which they formed. And I think that's the trend. If they're lone pairs to start with and they don't enter into a bond, then you put them into non-bonding orbitals at the same energy levels as they came in.